Hello, everyone. Welcome back. We would like to apologize for the small inconvenience we had before, but now we're live again, and we're coming up with our next three speakers. Things are getting exciting now. The next agenda will be, the first talk will be how to work smarter with chat and conversational AI. Then coming up next, using Google Cloud API to watch, visualize, and forecast the world in real time. And then humans versus AutoML, how to improve your ML models with BigQuery and machine learning by Polong Lin. So I'm going to introduce next host for this session, this block. This is Pranav and Markande. How you doing, guys?
Doing good, Ricardo. Hi, guys. For all returning speakers and new speakers, if you don't know about me already, I'm a second-year electronic engineering student studying here in Southampton, UK, and I'm also the co-lead for GDG Southampton. So looking forward to hearing everyone speak.
Okay, great, Markande. Well, guys, I'll let you through with the new speaker. Good luck.
Hey, Bruno.
Hey, Markande. So we would like to welcome Anu, who is here to tell us on how to work smarter with AI and conversational bots. So welcome, Anu.
Yep, hi, everyone. Yeah, thank you so much for having me. Yeah, let's get started. Sound good?
All right.
Perfect. Okay, so hi, everyone. My name is Srivastava. I'm actually based in New York, but I will be talking today about conversational AI with Google chatbots. So let's go ahead and start these slides. So who am I? I work in developer relations. So I work in cloud. I focus mainly on our AI and ML APIs. I've actually been at Google for actually pretty close to 7 years now. I actually started out in Android on infrastructure. If you were an Android app developer, I worked on GMS core. And then those core services use a lot of our Google Cloud services. And then I just was really interested in more cloud infrastructure. So that's how I ended up there. Just a fun fact, I am from Houston, Texas. That is also where Beyonce is from. So I will be talking mainly about Dialogflow today, but we're going to be showing chatbots in Google. And our chatbots in Google, you might have formerly known as Hangouts. Formerly, now as like a week ago, part of our G Suite, which is our family of productivity tools. So hopefully some of these icons look familiar to you, like Drive and Gmail. These are now rebranded as Workspace. I really like using these APIs in conjunction with the work that I do with cloud because these are tools that, not only engineers use, but like everyone at your company uses email and some of these other things. So you can bring your work and share it with people from all different types of job roles. So we're going to start out by laying the foundation of chatbots. I'll show you how to do a chatbot just straight programmatically. Then we'll use, we'll make it smart by integrating Dialogflow, and we'll focus on how to make it really robust and user-friendly and flexible. And I'll show you, I have a short demo, but I have a couple code samples. I'll do some demos, and I will send out all the resources at the end. So why are we talking about chatbots if they've been around since the 90s? Well, companies and consulting firms have done research and have data about how businesses can actually move more things into bots, which are more lightweight and easier to maintain and deploy than, a full mobile app. Some things, but not everything. So bots in Google. So chat is all about communication and collaboration, and it's even more crucial to us now that we're working remotely, so you're not in the office with your colleagues or you're not on campus, with your peers. So we're really trying to focus on bringing collaboration online. Okay, so now let's start the technical stuff. So the use cases. We like to group the main use cases for chatbots into 3 categories. So the first one is asynchronous notifications. You need to push some info. So, maybe you have a bot that augments your bug tracker, and then maybe you have a bug that's assigned to you that gets has a higher priority, or something happens. You could have a bot that actually pushes an alert to you to say like, hey, something happened. You might need to look at this. Next, we have one-off action. So I think the example here, we have is a project management bot. So maybe you can augment some of your project management work, like creating an issue and assigning it just in chat. So quick one-off actions. Last, we have querying for information. So some sort of lookup. The demos I'll show today are both query type bots. Okay, going even further. So how do we actually implement these bots? So the first and most common is HTTP and webhooks. So this is basically you have an agreed upon URL between your server and your chat client, and then you kind of go back and forth, pushing out, in our case, JSON to chat that chat knows how to render. Then in the middle, we have Cloud PubSub. Functionally, the code looks the same, but use PubSub as something in between to handle the messages and event streaming. PubSub kind of holds the messages for you, so you can push and pull the messages. This is really helpful if you need to work in between firewalls in different systems. Then last but not least, we have AppScript, which is a variation of JavaScript, but built specifically with libraries for Google products that has a lot more ease of functionality. AppScript is really powerful, especially if you're like working with spreadsheets. But of all these options to get a chatbot up and running in the shortest amount of time, AppScript is very quick for that. So let's start with our first demo. So this is actually a use case that came from work. I'm going to show you like a sample example of it. We have a bunch of sales team at Google's with a lot of account managers, and it can be hard to figure out who to contact if you have a question that relates to a specific account. We have an internal directory, but it doesn't really tell you like what people are working on, that week or that month. So honestly, a lot of my job is directing questions to the right people. So, if I need to answer a question about one of these clients, I'll probably have to open up this sheet. I have to remember where it is. And then, the next thing I'm probably going to do is just open another chat window and try to ping them. So it'd be great if I could just do this all in chat. I don't know about you, but I always have chat open. I'm always talking to my coworkers. That's just where we're doing a lot of our work. So how do we build this out? So I chose to put all the good stuff in a cloud function. So this is one of our serverless offerings. If maybe you've used App Engine before, that is one of our, our flagship serverless product. We also have Cloud Run, which is more new, but so with Cloud Functions, they are narrow, focused bits of code that you upload to Google, and then GCP figures out how to place and scale them for you. So we call this serverless because me as a developer, I don't need to know or care about, where my machines are, what's the uptime, when's the next time I need to do a security patch. So the placement and the scaling makes it a lot easier for the developer. So that is our server part. Where we're going to run the code. What's actually in the code? How do we look up the sheet? We can do that with the Sheets API. So this is an interface that allows you to do almost anything you can do in the Sheets UI, but programmatically. So since we're using functions in Node, this is the package I will need to install into my working directory from NPM, the Node package manager. So this is just a super quick intro on like what Hello World looks like for Sheets. Since I'm just trying to squeeze everything in 30 minutes, this is what the chat response looks like for this bot. And I have the code for this example up on GitHub. So this is what our first bot looks like. It starts out in a sheet. We've got a function to glue it all together, and then I can talk to, look up the information and share with my coworkers in chat. And all of these GitHub links will be at the end, and I can tweet it out later. So you saw that response, and one of the fun things that you can do with chat is have an interactive response. It's different than just like a regular text response. So we call these cards, and you can have headers, you can have different sections, you can have widgets and links and buttons. And what I think is really nice is that you don't have to worry about how these are going to render on different platforms. So it looks the same, whether it's on web or mobile, and you don't have to worry about, if like a tablet or a phone, it all renders the same. So yeah, here are some of the different types of widgets. And then these are actually just basic JSON responses. So here's an example I actually just pulled from the documentation. So that was the first example. It's a little bit watered down from what the real spreadsheet is that this use case actually came from. So this spreadsheet, it is from one of our European sales team. I scrubbed out the data, but it looks a lot more complicated. So the way that we really do this is like, we have different clusters, and then within clusters, you have people who have different specialties, and then these clusters actually handle multiple accounts. So what I would actually need is I need to know, okay, I need to answer a account question for, I scrubbed out the accounts and replaced them with Google products. So let's say someone from Firebase needs to know something about their account. So I first need to figure out, okay, who is in the cluster that handles the Firebase account. It would be cluster 1. Then let's say they have a question about security, and then I need to know the account manager. So you actually need 3 pieces of information and to look it up. So I could actually implement this the same way that I did that first chatbot, just write some straight node code. Maybe I expect all of those 3 parameters in a certain order. But, if I'm not using this constantly, I might forget the order, I might have a typo, and then it would be really frustrating to me as an end user. And we know that with technology, if something's too hard, people aren't going to do it. So this is where Dialogflow comes in. Oops. So this is a SDK that helps us parse out user input into parameters that I can more easily work with in code. So here's like just a quick example in the image. It takes this user input and then breaks it down into variables, date, city, duration, and those variables are much easier to work with in the code. So that's actually what we define as a conversational experience. I just love this graphic, so I just wanted to show it. Here's another example of it breaking down user input for like a weather bot. So will it rain today? That's a user's input. That's functionally the same as what is the weather today? Me as a developer, I don't want to have to hard code every single possible user type of input. I can't do that and then translate them all into this GET request. So that's what we get with Dialogflow. Here's some historical information about Dialogflow, multilingual. There's a web UI that I'll show in a little bit. Let's actually go ahead and do the demo. So I'm going to kind of do this in reverse. I'm going to show off this bot, and then we'll break it down on how we actually built it. Okay, so I at my bot, and then I ask the question. So I want to know, who is the account manager on Gmail for networking? Okay, phew. So I get back this card response, and I constructed this card to have a few pieces of information like the cluster that they're in, Maybe I have another system like Google Contacts where I can get their contact info and their location. This image actually, I use the Map Static API, and it's a really neat, pretty straightforward API where you can construct a URL request for a location, and then you just get back that image, and then I can use an image widget to embed it into my card response. So let's actually break down how we built it. So I needed 3 pieces of information. I needed the role, I needed the account name, and the specialty. So this is the Dialogflow console. This is where we can create an agent and train it to respond to the types of questions that we need. So let's start with the first thing you want to set up when you build a Dialogflow agent, the entities. So Dialogflow uses a pre-trained conversational model, but we have some words which are specific to what we need in the context of the spot. So things like networking, security, G Suite, those things have meaning, so we need to tell Dialogflow about them. So like I mentioned, we have account, role, and skill. I'll take a peek at skill. I think this is really important for making dialogue robust and flexible. So you can define synonyms. So if someone says Gmail, in the code, it'll actually show up as G Suite. And I can do things like fuzzy matching, which will be very forgiving if you have a typo. And I constantly misspell things because I'm typing really quickly. So those are the entities. Now we need to connect the entities to intents, what the user wants to do. So that's the action that I want to do with the chatbot. When you get Dialogflow out of the box, you always get you need to define a welcome intent and a fallback intent. So the welcome intent is what shows up when you add the bot into a room. Out of the box, you get like, hi, how are you? It's best designed to put instructions on how to actually use the bot here. Well, let's go ahead and look at where all the good stuff is for this bot. Look up Googler. So that is the action that I want. So we start with the actions and the parameters. So the parameters are those entities I just mentioned to you, the things I need as variables. So we have role, skill, and account. And to make sure I get all of these pieces of information, if I were to forget to say account manager or something like that, I could make them required and then have a prompt that would prompt the user to get that piece of information. So if I forget to put the role, I can say, hey, nudge the user because you need to know what type of role you're going to look up. So that's the next part. Then we need to train the agent on the types of input requests to expect from the user. So we've got some training phrases. Please tell me who's an engineer on Brain. When you type these in, Dialogflow will actually try to see what the parameters are, and you can tweak these. And you want to have a lot of training phrases to make sure that your bot is as flexible as possible. So that was a lot of the setup. Where does my code go? Now we go to the Fulfillment tab. Yes, I do want to navigate. So this actually does look structurally very similar to that first bot. We are using a function. This one just happens to use a Firebase function instead of a regular cloud function. Both really similar. In my case, we're both using Express. Here is where I import the Sheets API. Like I said, Firebase functions. I have some code that looks very sheet-like. Basically here, I have the Dialogflow agent. And then from the agent, I'm able to get the normalized parameters that the user gave me. So I don't need to worry, what order the user put them in. Did they misspell something? Did they capitalize it? Did they not capitalize it? The agent normalizes all of that for me, and then I can just plot those parameters, construct a Hangouts chat response, and then push it back to the chatbot. So this example, just I chose to only show it for Hangouts chat, but you can actually use the same Dialogflow agent to serve multiple different types of bots. So we have some enterprise options here. I could actually, I could support Twilio with the same bot. I could support Facebook Messenger, Slack, just by enabling here in the integrations page. So yeah, I didn't really show much of the code, but again, I have it all on GitHub, so I'll make sure that those links are sent out later. Oh, one last thing I forgot to mention. What I really like in the console is you get Google Assistant for free. And then you get this little thing here on the side where you can actually test it out while you're tweaking the agent. So here's one I ran a little bit earlier. Who is the account manager for networking at Waymo? This is super helpful for debugging because you don't have to wait to deploy your bot every time you want to make a change. It'll show you what intent it matched it to, and then it'll actually show you what those variables were translated to. So this makes it really easy to iterate with your agent. Okay, so I think I have about 10 minutes left, so I will finish up the slides and then leave some time for questions. So as I mentioned, this is what I think the juiciest part of the agent is you have the agent, and this is exactly how you get those variables out that are parameters. So this bot, it only had one intent, but more likely than not, you're going to have a lot of different actions that you want your bot to handle. Each intent is made of at least these parts: training phrases, actions, parameters, and response. You can have multiple intents and chain them together, and it creates this cycle. Here's another example that we like to use a lot. Maybe you have like a banking bot. You could have like the first intent, which is checking info, and then that chains to checking your balance. And as your bots grow, these do start to get bigger and more complicated. There are other alternatives to Dialogflow for enterprise context. CCAI and then CX was just launched. So let's recap what we built today. So we started with a tool that our coworkers were already using. People were using the sheet. We don't want to pull all the information out. We don't want to make it difficult for them. We just want to use what they're already using and then just make it easier. So then we trained an agent to handle the natural language questions and sort them from the sheet. And then directly in the product that they were already using chat. So no need to open a new tab and wait for it to load. Try to remember how to use it. Just using it directly where you are, where your next action is probably going to be opening another chat window to go talk to that person. So then we also augmented it with some other Google services. You can really do whatever you want in that cloud function. As I mentioned before, I really like the static maps API to make it a little bit more visual. I can know where that person is. So that's what I used. Also, using Google Contacts to look up, where that person is located, their email, other pieces of information. But you could really put, whatever you want in here. Maybe you use another directory service, or maybe there are some other, like your project management API that you want to integrate with. So yeah, here are my links on how to get started today. These were some of the things that I did to get started building this once we had the idea. We've got the Dialogflow Basics, which is a great tutorial, some code labs, also the quick starts for Sheets and Hangouts. Here's a full working code, and then please let me know if you have any suggestions. Any feedback on the documentation or anything, you can definitely tweet out at me. And on the GitHub, so I showed you a lot of setup and configuration in the Dialogflow console. You can actually zip all that up into this config and then download it and then upload it into another Dialogflow agent. So I actually have the config zip in this GitHub repository, so you can download it and then just plop it into your Dialogflow console and actually test out the bot without having to, recreate everything that I showed. So yeah, please let me know if you have any questions. I've got a few minutes to answer them. If not, definitely please find me on Twitter.
Thank you, Anu, for that very informative and detailed talk on how to use conversational AI, and I thoroughly enjoyed that. Over to you, Markande.
Hey, thanks, Pranav. Really, it was a lovely talk, and it just tells us how endless the sky is. We can just explore anything and make things easier for us. Thank you so much.
Yeah, thank you.
Okay, so ever wondered how would it be to analyze, visualize, or even forecast the real world for now?
No, I haven't, and that's why we have Dr. Kalev here to talk about that. So please welcome Dr. Kalev.
Thank you so much. It's great to be here today. And can you all see my slides?
Yeah.
Not yet. I think I can add it to stream. Yep, now we can.
Great. All right. Well, thank you so much for having me here today. It's great to be here with all of you. So this image really summarizes the focus of my work, which is really about this idea of using massive amounts of computing power to try to scoop up the world's information and understand what's happening about our world, essentially the global heartbeat second by second. So, starting with this idea of news. So, specifically, how do we take the world's news information and transform that into data to take, whether it's in spoken word format, in video, in imagery, in textual format, in all the different ways that news comes? How can we use massive amounts of AI power to essentially translate that into a codified form that we can actually extract insight from to understand world events? So, of course, it all begins with news. But if you look at this image, so this is actually all the places that my project, the GDELT project, has gathered information about over the last X number of years. Now, what's so interesting about maps like this is, of course, oftentimes so much of the work that's done, especially in the traditional AI field, focuses on English. But of course, we live in a rich multilingual world. And so the GDELT project actually live translates absolutely everything it monitors in 65 languages from around the world, soon actually to be about 100. And one of the things that makes this so interesting, there's actually a company up in Canada, Blue Dot Global, that actually sent one of the earliest alerts of COVID-19, actually back in December 31st, using our data, because we're monitoring local media across the world, including local Chinese language media in Wuhan. And what we do, of course, is we translate this material, we process it, and I'll get to all the different things we do with it, but we process all that material and generate essentially a codified metadata annotation over the world's media in real time. And in turn, this company up in Canada, they built a set of machine learning models that take that feed and basically analyze our codified representations of this material and basically scan it to see, is this what would happen if another pandemic occurred? Or is it a look back at things? Or is it something that appears to describe something happening now? And if it is something that's happening now, does it appear to be something that might actually have potential to go viral, for example? And so that's actually a really interesting story. And actually, what makes that story particularly interesting is back with the Ebola outbreak, actually in 2014, we were starting to do a little bit of machine translation, but at very small scale. And in our postmortem, we actually turned out that we had actually gathered the earliest glimmers of the Ebola outbreak, but we hadn't been able to translate that. And so again, leveraging the power of machine translation to be able to essentially lie. And that's what also is quite fascinating to me is we're actually at this point today where machine translation is good enough that, again, it's far from perfect, but it's good enough to get that general gist, to take absolutely everything that we're monitoring around the world in these 65 languages and translate all of it. And with a quality that's good enough that we can actually understand the basic gist of what's happening around the planet. That is a really transformative moment. And so why, of course, you might ask, well, why bother studying the media? Well, we can do all kinds of interesting things. We can map world events in real time. We can look at things like mapping narratives in real time. So going beneath what's actually happening to what people are saying about that around the world. So how are they reacting to that? to understanding the emotions around that. Is this being portrayed as a good thing or a bad thing? And what's particularly interesting about data like this is, we're not measuring what people actually feel. We're measuring what the world's news media, is saying about those locations. So this particular map you're seeing right now, this is actually created. We actually do this each year, and we actually have a live version of this actually an animated version that goes day by day over the last, I think, half decade. And what we do is, for example, we take all the news articles around the world in a given day that mention Paris, for example, Paris, France, and we look at the average emotion of all those references, and we put a dot in the map from bright red for very negative to bright green for very positive. So what this is very fascinating is you're essentially crowdsourcing the world's media to see how they portray places around the world. And this becomes very powerful because it allows you to kind of understand what's the world saying about the different parts in the world. For a lot of people that haven't necessarily traveled the world, and of course, very few of us have seen everything around the world, to be able to understand, like, what is the world's media saying about it? To even more important things like nowcasting and forecasting, to be able to actually take an event that's breaking in real time and be able to track that second by second, what's happening, and even be able to forecast the future, to be able to say, what might we expect in the coming months and years? So what makes all this possible? Well, of course, Google Cloud Platform. So we use many different aspects. So the GDALT project is really this idea, gdaltproject.org. It's this idea of scooping up the world's information and using massive computation to try to understand it. So, of course, we use Compute Engine. We use all the different storage technologies. But in the lower right there, under machine learning, so we use the Vision API to be able to look at all the imagery. Because, again, news is so visual first these days. So we use the Vision API to peer inside of all the world's imagery. The Speech API. So, of course, radio news is very important around the world. So being able to transcribe radio broadcasts, and also, of course, television broadcasts, being able to transcribe that. The Video API to be able to understand the visual landscape of news. The Natural Language API to be able to understand text. And of course, with that trio, we have we actually have the big three modalities of news. And of course, the Translation API to be able to translate material from around the world. But what's interesting is, the output of those APIs, for those that have done a lot of work with AI work, is just enormous reams of JSON annotation data. So, for example, you hand a video over, and what you get back is frame by frame annotations of what's in there. It's incredibly rich. But how do you extract insight from that? How do you go from annotating, millions and millions of minutes of video to extracting high-level insights from that? So that's where things like BigQuery and Inference API come about, and I'll get into all that. So let's start with text, since that's, of course, the simplest modality here. So we have something called the Global Entity Graph, powered by the Natural Language API. So each day, we take a random sample of the news coverage that we monitor around the world in 11 languages, which is what's supported by the Natural Language API right now. We also take, of course, captioning. So television captioning, radio ASR, OCR, text from on-screen television, essentially anything that comes in textual form. And we feed that through the GCP Natural Language API. And we do a bunch of different things. Of course, we run that through BigQuery, we run that through Inference API. What you're seeing here is a neat little graph. We actually ran a volume of news coverage through it and asked it, what are some of the central elements, some of the central entities that are extracted from that, and how are they all interconnected in terms of co-occurrences? Of course, we also have the dependency graphs there, so we can do some really interesting things. We've done some interesting Q&A work. So one of the things, once you have those dependency graphs that show how all the different entities are connected through the verbs, you can do interesting things. For example, we have a demo where we ask, did Donald Trump ever meet Al Gore? And, simply by taking that, layering that onto the dependency parses of all this news coverage that we've processed to date, you instantly get back yes. And here is the actual description of their meeting. Or we can do narrative assessment. So, for example, has climate change contributed in some fashion to the wildfires in Australia? And if you ask that, it's actually very interesting. You get back three major answers: yes, no, and maybe, unsurprisingly, when you aggregate the world's news. But what's interesting is you can take an outlet, say, like the BBC, and you can actually see that all three of those narratives are present in the BBC's coverage. We could actually isolate, using, again, those dependency graphs, we can actually isolate the argument structures that are being made in news coverage across each of those dimensions. So there's a tremendous amount of ability to understand, to essentially codify news in ways that we can understand high-level meaning from. But what's also interesting, when we think about understanding text, we oftentimes, when we think about natural language understanding, we tend to focus more on, again, on these Q&A types of questions. what's really interesting is when we think about these higher level questions, not just traditional Q&A in a search, for example, metaphor, but understanding language. So this is actually, we've taken the part of speech role and dependency parses of a set of languages, the 11 languages supported by the API now, and we can actually ask these high level questions. For example, what's the part of speech breakdown by language? Which languages tend to have more nouns than verbs? And of course, any grammatical expert can teach you these things, but here we can actually observe them in real life. So for example, we have, and again, everything here I'm talking about is all open data. You can go right now to gdlproject.org, download all this data. It's available in BigQuery. So you can download the JSON files. You can go access them in BigQuery. We've got tons of examples of all the different types of analyses you can do with this. But part of speech tags are very interesting because, for example, you can ask the word impact, at least in American English, is known as a noun traditionally. Is increasingly being used as a verb. So for example, we've worked at Linguist to understand we can go through this data and say, find me every instance where the word impact was used as a verb. And what was the context? What was the clausal formation of that? We can also do really interesting things using those dependency parse trees. We can start looking at argument structure of the global media. One of the things that we're really interested in when it comes to mis and disinformation is this ability to ask, for example, let's take an example of aerosol spread of COVID. There's right now an argument within the public health community of does it spread through aerosols or not? What we want to be able to do is not render a judgment on that, because again, that's for the health experts, but to be able to say, take, for example, here in the US media, what we want to ultimately be able to do, and we're still working on this, is to be able to process all of that media each day in the US and be able to extract out and say that when it comes to, say, aerosolization, there are two argument camps. One says yes, one says no, and here are the structure. Here are the outlets that are making this argument. Here's the ones that are this. Here's the sources that they're citing as truth for that. Here are the counter arguments they're citing, and here's sort of the cross linkages among that. That ultimately is what we want to be able to do, essentially a narrative diagram. We're not quite there yet, but the tools, the basic building blocks are present through things like the Natural Language API and some of GCP's other AI things, such as some of the examples in AI Workshop. So again, it's this ability to really start stepping forward, to really try to understand, to allow machines, again, a lot of these are holy grail things, but we're trying to take those first steps towards that. Now, of course, when it comes to news, imagery is huge. I mean, we're increasing an image first, a telling of the news media. We don't, you don't, for example, today read a news article about there were protests in this area or there was an airstrike here. You see photographs of it, which means that we need to be able to actually understand imagery. So we have something called the Visual Global Knowledge Graph, again, powered by Google's Cloud Vision. So what we do each day, we take a random sample of news imagery from across the planet, all countries. Today, we've run about 500 million images through Google's Cloud Vision. And what we do is we enable most of the features. So labels, we ask it for all the objects and activities that are in that. OCR, I think OCR is maybe 300 plus languages now. It's incredible. Geography, facial motion, and then we also extract out EXIF metadata. We also have it do a reverse image search. So this becomes very powerful. Reverse image search is particularly, that's the web entities in Cloud Vision parlance. That's particularly powerful. Essentially what it does is it takes that image, it does a search across all the imagery that Google has found, and then it looks at the captioning, where those images were found on the web and how they were captioned when they appeared on the web. And this becomes very powerful because, for example, let's say that an image appears right now. It says, this is a live protest in Paris 10 minutes ago. Well, we can take that image and say, well, this purports to be right now. I'm being told that this is a live image, but actually this image has been around for about 10 years now on the web. It's traditionally, captioned as Berlin, not Paris. And actually that's German text in the street signs behind there. So this ability to do very rapid triaging is incredibly powerful in terms of verification. And we can do all kinds of fascinating things. We can look in the back, we can actually use Safe Search to look in the imagery and say, well, is this tagged as violent or not violent? Now, in the news parlance, what this is actually a very powerful map you're seeing right here. Here in the US, when we hear about things happening around the world, we see a very sanitized version of the media. So for example, here with the refugee crisis, we don't really see any images of hardship. We see mostly just statistics, tables of numbers, maybe presidents at podiums talking about the fact that there's a refugee crisis. We don't actually see the human impact. It's very, very rare here. In other parts of the world, you actually see the live impact of policy across the world. So for example, the refugee, you actually see what it looks like in refugee camps. You see the arrivals. You see what people are going through. Does that change people's perspective when, suddenly it's not just a table of numbers and a newspaper headline? You actually see the real human faces behind it. So this is very interesting when we think about how we're perceiving the world around it. And specifically, do we see news coverage around the world through the lens of the people being affected versus just, an image of a desert, for example? We can do all kinds of interesting things with facial emotion. But this is very interesting. Remember, Google Cloud Vision does not do facial recognition. What it does do, though, remember, it goes for those image captions there. So we can say, find me all the images that were captioned as Donald Trump, and we can make a fascinating map. And in the right hand, there's a really interesting one. This was at a moment when China and the Philippines were having kind of different views towards Trump. And you see the Chinese one, you see that at the time period, they were not as happy with Trump. So you see kind of a haggard Trump, a laughing Pope. The Philippines read the exact same image, but inverted. And so this becomes very fascinating as we can start understanding visual narratives. That's something we've never been able to do before. So say, for example, taking all the images captioned as something and help me understand, kind of how something's being portrayed, like climate change. What's the imagery? And actually in climate change, what you see is the imagery of climate change is no longer polar bears, it's deserts. It's really refocused from the impact in the natural world to the impact in the human world. And we can do things like verifications of floods. So we can say, find me all the flood imagery around the world. And verify this. So if I have a news article, it tells me there's massive flooding somewhere. Well, what's massive? Does that mean a couple inches of water? Does that mean the whole downtown's deluge? This ability to look in real time and do sort of assessment of global events. We can also look at the background. This is actually an interesting repurposing of an API. So we've worked a lot with the environmental community, and they're very interested in understanding the environment around the world. So we look in the ground, in the background of every news image, we look in the ground. What you're seeing here is all imagery that appeared in the news. And we look in the background and we say, is there trash in the ground? We look in the sky and we ask if there's smog in the sky. And by doing this day in, day out, every day, you can start essentially understanding the daily the sort of the daily rhythms of a country. It's very experimental, but it's kind of this idea of what if we could rethink how we reimagine essentially how we think about what news material tells us, where, a president at a podium is one thing, but let's look in the sky and the background of each of those images. What do we see there? Can we use that to understand things? Try and, for example, geolocate all this imagery. This is very interesting when you can start actually positioning imagery on the screen, but we can also do very interesting things like visual clustering. So, for example, we can remember all this 500 million images we've annotated, we have the objects and activities that are depicted in each of those, about 10,000 or so that we found to date in global, actually, I think 30,000 imagery, about 10,000 in broadcast. And so we can cluster that. We can say, what are the objects and activities, the labels, if you will, that tend to co-occur the most? And we can look at different dimensions of that. We can look at different countries, different levels of clustering, and starting to understand the visual narrative. So, for example, if you take sports imagery, what are the dominant themes that we see in sports imagery compared to, say, technology imagery? This becomes very interesting as we can start looking country by country and look at, for example, transportation is very interesting if you look across the world. In some countries, when you see coverage of transportation, it's public transportation, buses and trains. In other countries, it's military hardware or governmental equipment. In other countries, it's civilian vehicles. In some countries, it's more luxury vehicles. It's a really fascinating thing when you see about, like, when I open up the news in my country, what am I seeing? What's those visual narratives that I'm seeing day in and day out? But of course, still imagery is very, very powerful, but video is intensely powerful. Television, which we've never really been able to do before. So we actually look at video, at television news through two different lenses. So one is through closed captioning. So in collaboration with the Internet Archive's Television News Archive, we look at the closed captioning of about 150 stations. So that allows, we actually have you can actually keyword search that in real time. So you can actually ask how often is this particular topic being covered. But we also, again, remember, run that through the natural language API, which does some really interesting things. So here in the US, two politicians get on stage, they're addressing each other, senator. It's actually able, because through CoRef, it actually tries to estimate which one of those people is being referred to in each of those. So you can do really interesting things. For example, look at Beirut, how that's being covered on different television stations. One really interesting word here is that automatic speech recognition. Historically, you had to speak very slowly. It was very inaccurate. Google's speech-to-text ASR is incredible. We've been doing a lot of work comparing this to human captioning. So for us, we have the human-generated captioning for each station, where literally an actual human sat there typing in real time what they're hearing. And we're actually finding that Google's ASR for both video and speech-to-text is at least as accurate, and in most cases, orders of magnitude more more faithful and accurate. And faithful is a really interesting one, because oftentimes people will speak fast on television and the human can't keep up. So there'll be dropouts. So, and this is actually interesting. There was a congressional testimony here in the US not that long ago, where a bunch of senators and different people were testifying, and they were speaking very fast. And the human transcripts have huge gaps there where the people were going so fast and they were speaking a very technical legalese language. And the transcription is just, there's huge blocks where there's just nothing. The transcript is missing. Again, Google's ASR just fills all that in. And what's also interesting is on the human transcriptionist, when you introduce someone, you say, here's the ambassador to Estonia, for example, my Estonian heritage, that's missing. It'll say, here's so-and-so, and the human won't type in the honorifics or the affiliations. Again, the machine's picking all that up. The machine is far more faithful to that. And so this is a really fascinating thing that we've reached that point where ASR is that good. But of course, with video, what you're really interested in is the visual dimension of it. So again, in collaboration with the Internet Archive's Television News Archive, we're non-consumptively analyzing ABC, CBS, NBC Evening News, BBC News London, CNN, MSNBC, Fox. This actually should say January now. And actually, we have a large project. So again, all open data, all these annotations. And we have actually from January to this year, 24/7, and then in periods of major disease outbreaks from the past, which I'll get to in a second. And again, the JSON's available. It's available in BigQuery. And we actually have an interactive search engine where you can actually search those labels. You can do really interesting things. For example, you can ask how often bookcases appear in television. One thing that's very interesting is the machine is annotating frame by frame. Versus humans, we tend to, when you have humans annotate television news, they do it in seconds of airtime. So sometimes it's disjointed. So there's actually an example of a commercial that appeared on television news, 5 different visual narratives in the space of 1 second. The machine is frame by frame. It captures all that, versus humans tend to kind of lump things together. So if you're combining traditional human workflows and you're starting to use machines, there's going to be some interesting questions of the machine is so precise in how it annotates that, there's interesting questions of how do you blend that with the imprecise human annotations? How do you think about that? Google's Lauren Picard did a very interesting one using camera changes to generate visual summaries, and we've done some interesting work around that. But oftentimes for television news, you want to segment shows. So take, for example, a 30-minute broadcast about COVID around the world. We want to say at the highest level, this is a COVID broadcast. Then we want to say, here's the section on COVID in Europe. Then here's each of the sections about each country and the sub. So essentially, we want to take a half-an-hour broadcast and break that into essentially a tree diagram. So we've been doing a lot of work. Google's AI workshop, which I highly recommend. They have all kinds of really fascinating cutting-edge work there. So one of them is semantic similarity for natural language. So you take each, in our case, each line of captioning, and we ask, is this line entailed by the line that precedes that? And you get essentially a probability score there. Using that, we can actually generate these fascinating graphs, essentially, splitting a broadcast into a set of narratives. Now you can do all kinds of interesting things. So we can ask where there's podiums. We can ask for bookcases. This is actually a really interesting one. When we ask the inference API, that's one of Google's tools. What is different about COVID era material, COVID era broadcasts versus prior broadcasts? Very first thing that popped out is bookcases. And, you're looking in the lower right, because everybody on I'm kind of an exception here, but, on television, everyone's got bookcases behind them. That is the visual narrative of the COVID pandemic. Now, what's also interesting, and of course, BigQuery, you can do TF-IDF calculations and do all kinds of fascinating affiliations there. Remember, Cloud Video is actually doing motion OCR. And so, for example, the lower right, so this is actually really interesting, where we have an ABC broadcast with Arabic text there. Again, the machine just perfectly picks that up. We weren't expecting to see that, and it just picks that up. You've got in the lower right there, green text over red noise with a yellow crosshatch background, kind of worst case scenario for OCR. Flawless pickup, machine-generated OCR, of course, motion OCR. So you look in the Chiron, the text in the bottom of the screen here, it says no more, you can't see what that text is if you captured it midpoint. Again, because it's motion OCR, it was able to look before and after that and correctly recover what that word is. We can, again, look at the OCR text and ask, for example, so CNN runs their COVID dashboard 9 hours a day. We can actually use the credit there where it sources the credit for that information. And we can actually then generate a heat diagram like this of every hour, how many seconds of airtime in that hour was that credit line on screen. Again, by using the OCR, because Cloud Video is OCRing every second of that airtime, we can use that to do really interesting questions. we can actually pull. We actually just released this morning a data set of all of Trump's tweets that were found on television news, again, using the OCR to pick out all the appearances of his tweets on screen, and then combine that against Twitter to actually reconcile the Twitter ID for each of those. So that's actually a data set we just put out this morning. But let's say you want to know who's telling the COVID-19 story. Doctors, a lot of medical professionals. So again, using a simple regular expression in BigQuery, we can simply say, find all the occurrences on screen of text with the words doctor, space, and get me the next two words. So, for example, here's Dr. Daria Long, Dr. O'Neill here being interviewed. And this is really fascinating where, again, by simply saying, take that on-screen text, find the words doctor, find the two words that follow it, we actually make a histogram day by day, station by station, that actually gives us all the doctors that are being interviewed on screen. So we can actually say, like, who's telling this story, essentially. We can look at the number of characters OCR, we can look at entities per second, we can do visual similarity. Again, one line of SQL in BigQuery, and we can say, take by day all the entities that are on screen on each station. How similar are they? Now, the top one there is very interesting. That's actually showing American television news is very similar. We can actually see it fracturing apart. And there's some really interesting stories as to why that happens, and then it comes back together again. It has a lot to do with the partisan nature of our politics here in the U.S. The bottom graph, though, is very interesting. So you can see in the bottom graph, there's a sudden hard deviation and then back to normal again. That's actually anomaly detection. So there we actually found that a set of broadcasts were very, very divergent from everything else at the time period. And we were able to go back and see that actually what had happened is the stations that we were monitoring for those broadcasts, our local video provider had actually changed the station numbers on those. And so we'd actually gotten incorrect material for that. And so again, that's not something you ordinarily be able to easily detect, but just comes out starkly in the data. Of course, finally, radio, we can do really interesting things. So again, with ASR of radio, speech recognition of spoken word, this is actually an interesting example of mentions of COVID-19 on BBC News London, which is television, of course, BBC World Service for the international audience, and BBC Radio 4 FM. You can see kind of this early stair step, and then you can see kind of this fracturing where the domestic radio has been covering COVID a lot less. And so we can do some really interesting things there. And then finally, we have something called the Media Data Research Consortium we're collaborating with. So they actually have a large Google Cloud COVID-19 research grant quantifying public health. So what we want to understand is how COVID-19 is being covered in the news. And so this is a massive data set that's actually just been released. Radio, 10 US stations. We have, of course, the television, web imagery, about 2 billion articles, 152 languages. But for television, we've annotated everything on BBC News, CNN, MSNBC, Fox this year, all this entire year, second by second for COVID-19. And then each of these past disease outbreaks, and all these annotations are available. So you can start asking, how has COVID-19 been covered compared to previous disease outbreaks? And then finally, the global relationship graph. One of the final things that we're interested in is how do we, again, go from this fire hose of information to actually codifying statements. So we can start looking at things like contested statements, for example. So thank you very much. I know I've covered a huge amount of ground today. But essentially, the short version of this is, the GDELT project, which you've got the URL there. You go there, all the data I've showed is all open. Essentially, every day we're scooping up global news material, radio, television, print, broadcast, television, still imagery, all the different modalities, 152 languages, 65 live translated, bringing all that in, processing that through all of GCP's AI APIs, taking those annotations, running through BigQuery, Inference API, all these different tools in the GCP platform, and then using that to extract high-level information, to try to understand the world. So again, if you're interested, say, in what video annotations look like, you can download right now entire year, 24/7 of annotations from Cloud Video and see, what does this actually look like in real life? How might I use this in my own workflows? Let's say you've got some video, you can use this to prototype and say, what would this look like? What are the types of new insights I can extract from this? So thank you so much, and go to gdeltproject.org, just gdeltproject.org. Everything's there. Thank you so much for having me.
Thank you, Caleb. I thoroughly enjoyed that. And one thing that I realized after hearing your speech is that this is the closest that we will be to modeling human languages and nature. But yet in the future, we will have, of course, new ways to model human nature. And as you said, something else that I found interesting about your speech is that the GDELT project involved 3.2 trillion data sets, which is the largest ever data point set that was ever collected in the world. So that's what I got from that, and I thoroughly enjoyed that. Over to you, Markande.
Hey, thanks, Pranav. I never imagined how a simple news article can be used to derive such insights. Thanks for the deep insights on the topic, Dr. Kalev.
Thank you.
Yep. Thank you, Dr. Kalev, and we hope you have a great day. And once again, thank you for the speech.
Thank you for having me.
All right.
Okay,
and
coming up.
sorry, go ahead.
Go ahead. Okay, coming up, we have Polong from Google to give us some great tips on improving the machine learning data models. Hi, Polong. How are you?
Hi, Polong.
Hello, I'm streaming in from London, UK, so hope everyone is doing well.
That's great. I also heard you're from Canada, but right now you're based in London. So how's the experience?
It's so far so good. It's great here in the UK, but I do miss Canada sometimes. So
Right, that's good to hear that. So if you're ready, I will share your screen, and as you can see the time, you have a bit of extra time. So yeah, feel free to take your time, and good luck.
Great, thank you so much. Excellent. So hello everyone again today. My name is Polong Lin, and I'm a developer advocate for Google Cloud. My focus is on data science and machine learning on Google Cloud, specifically around BigQuery ML. So today I'll be talking to you about humans versus AutoML, how to improve your machine learning models with BigQuery ML. So in terms of the focus of this talk today is I'll talk about kind of introducing what BigQuery ML is to you if you're not familiar with it. But more importantly, the bulk of the session today will be focused on how to improve your models with BigQuery ML. There's a lot of pre-processing functionality within BigQuery and BigQuery ML, which allows you to hopefully improve your model. So I'll go through some of the steps related to that. And then finally, I'll show you how I compared against AutoML and how some other humans compared against AutoML at the very end in a Kaggle competition. So there's some assumptions I'm going to be making based off of the audience. I'm going to be assuming that you are already familiar with BigQuery, that you are familiar with SQL as well, but that you are new to BigQuery ML and you could be new to machine learning as well. So this is hopefully kind of driven to the right audience here today. So just a quick overview. So hopefully you will already be familiar with this. Google BigQuery is the fully managed serverless data warehouse on Google Cloud. So it's petabyte scale. You can put in a whole lot of data, as you heard from the previous talk. So Google BigQuery is really this phenomenal kind of scalable product that allows you to really analyze data at really kind of extremely fast speeds and at scale as well. What's really interesting is now you can run and train and deploy machine learning models directly on BigQuery just by writing in SQL. And so that is a step forward in terms of data scientists working with data on BigQuery. So I'll be talking about how do you actually build a model in BigQuery ML, and then how do you improve your model in this talk today. The focus of the talk is actually going to be around a single problem, and this is a kind of a problem that I kind of came up with. There's a data set that's based off of that is a public data set on the Google Merchandise Store, which is actually a real e-commerce store out there. You can actually buy some Google branded products if you like. But behind that, there is Google Analytics running. And so there's anonymized data that's being hosted publicly on a BigQuery public data set. So using that as a basis, I created this kind of problem around this online retail store, the Google Merchandise Store. Can we use the Google Analytics data, the user behavior data, to predict if someone's going to add something to the shopping cart just based off of that kind of Google Analytics data alone? So let's take a quick look at the schema on BigQuery. So I'm just going to stop my screen share here and then share my screen again with the BigQuery tab here. And so hopefully you can now see my screen, and you should now be able to see my BigQuery tab here. The focus here is just going to be on the preview here at the bottom, so you kind of get a little bit of familiarity with the data set that I'll be talking over. So first, in every row, we have kind of a session by a particular visitor on the Google Merchandise Store. We have the visit start time. You can see this is in an integer format, so that's going to be a Unix epoch time. We also have the date, so this is year, month, day, but something's kind of funny with the hour, minute, and second, and it's all in a particular time zone as well. We also have some categorical variables. So we have the device category, how they visited the Google Merchandise Store, whether it was from a tablet, mobile phone, desktop, or whatnot. Is mobile, did they use a mobile phone? True or false? Operating system, iOS, Android, etc. Browser, Safari, Chrome, etc. country, United States, and so on. City, sometimes not available because, again, this is anonymized, so it's trying to, not reveal everything. Traffic source, traffic medium here, traffic campaign, and these are all text-based or string-based or character-based columns. So that's a good thing to kind of keep that in mind as we create some features later on. And then a bunch of numeric columns as well here. So you can see is whether or not this was their first visit to the website, is bounce, did they leave right away, total visits, total hits, the number of actions they took. So that's the total number of hits they did within that session, total page views, the total time that they spent on the website. That's probably an important one, right? Total time on site, total transactions, total product pages viewed. And then finally, and most importantly, is added to cart. So 0 if they didn't, and 1 if they ended up adding something to the cart. And this is just the training data. So you can imagine the testing data that I use to evaluate this is based off of a completely separate data set that doesn't have added to cart. So that's kind of the problem that I framed. So let me quickly go back here to my slides. And that is let me just go back here to here. And let's continue on with the actual BigQuery ML modeling. So the very first thing when you're trying to build a machine learning model is we have to have the training data. So, given a very simple select statement, select full visitor ID, the country, the total page views, and then finally add it to cart from my project.dataset.train. This is, fairly simple. This is something that anyone should, be comfortable doing in BigQuery already. So assuming that this is, the training data, just by adding in a couple more lines of code, so create or replace model, we can now create this model directly within BigQuery. So this is a BigQuery ML model. And so just kind of going through this line by line here, we're creating the model within this data set. So my data set here, and we're giving the model a name. So in this case, I'm going to be creating a logistic regression model. So I'm going to be calling this logreg or logreg or however you want to pronounce it. And then under the options, I specify the model type. So here I specify logistic reg. And then the variable that I'm trying to predict, which is the added to cart column. And of course, because the full visitor ID doesn't actually mean anything in terms of the modeling, so I'm going to be commenting that out so that I'm only essentially training the model just on country, so where they visited from, and also the total page views that they spent kind of during that particular session. And then finally, of course, added to cart, because we have to have that in order to train the model. And this is, again, coming from the .train. This is the train table that I kind of set up. And so the next thing that I can immediately do is ml.evaluate. So get the evaluation metrics of my model directly. And so you might be thinking, so hold on, there's two things. Number one is, where is this model? Well, the model is actually an object sitting within my data set. So that's already there. It's within BigQuery Run. It's already hosted. So I can begin to use it. I can begin to evaluate it directly. And the second thing is, wait, hold on. We haven't really set up train and test before. So how are we exactly evaluating this? Well, it turns out with create or replace model, going back a slide here, it automatically splits your data into train and test, or train and validation, so that when you run ml.evaluate, it's actually doing that evaluation on that kind of part that it kind of held out during your training phase. So because it does it automatically, you don't have to worry so much about train and test split. Although if you really wanted to, you could set that manually if you like. But this does it automatically, and I'm happy I'm saving an extra step here. So I can run ml.evaluate, and I can kind of evaluate my model. And then if I want to actually evaluate my model on the actual test data set, this is how I would go about doing so. So using the exact same syntax here, but simply specifying after the model is the test data set that I want to actually that I want to evaluate the existing model on. So suppose that our evaluation metrics are pretty good. It's performing quite well. Then the next step is, of course, to make predictions based off of the model. So in this example here, I'm selecting certain columns here from ml.predict model, and then the model name, and also based off of the data set or the table that I want to predict on. So here I'm just selecting these two columns. You could do select star. There's lots of different kinds of columns, like not only the prediction but also the confidence as well. So there's lots of different columns, but in this case I just simply chose to use two of them there. But simply with this ml.predict statement, you can now essentially use your models and make predictions on data that's sitting in BigQuery. So that is BigQuery ML. That's how you create BigQuery ML models, and it's very simple. Just these 3 or 4 steps here. And you might be wondering, what are the other kinds of models that are available with BigQuery ML? Well, depending on the category, so for classification, you might have logistic regression that you want to do, or you could also use XGBoost, or deep neural networks, or AutoML tables. for classification. For regression, you can use linear regression, XGBoost for regression, deep neural networks, and AutoML tables for regression as well. For other types of models, you can use k-means clustering. You can do ARIMA or auto-ARIMA with time series forecasting on BigQuery ML. And then you can also build recommendation systems, whether you have implicit or explicit feedback. You can build these matrix factorization models with BigQuery ML. And then finally, if you are someone who likes to create your models in TensorFlow, you can actually import those TensorFlow models directly into BigQuery ML, or rather into BigQuery essentially, and then run your models on the data that's stored on BigQuery. So that's a great kind of direction going into BigQuery in a way. But going the other way, so you can actually export your models as well. If you want to host your models online, you can export your models from BigQuery ML to be hosted online on AI platform. So I've mentioned AutoML tables. I'm curious as to what exactly this is. So AutoML tables helps you kind of create really great models very quickly with just essentially one command. At least in BigQuery ML, it's a single command and it's very, very easy to run. But what's happening is it's actually going to be searching through lots and lots of different kinds of machine learning models to try to create the best possible model for you, so you don't have to be an expert data scientist necessarily to be able to train the best possible model. AutoML will try to search for it for you, and it'll attempt to create a very, very good model. It also does a lot of extra kind of neat things as well here. So it does automated feature engineering for lots of different types of data. It also has resiliency, and it creates guardrails for imbalanced data, missing values, outliers, and so on. So lots of different ways in which you can kind of just almost throw your data at AutoML and have it create the best, potentially the best possible model for you. So let's go back to this problem of this online retail store. Again, we're trying to predict the shopping cart, added to cart, 0 or 1 as a probability, right? So let's try to go through the various steps of training different models, changing up different parameters, changing up different things, and try to improve our model. And what we'll do is we'll try to see how the score kind of improves over time, or whether it kind of decreases over time as well. So again, this is this training data set here is 765,000 rows of data, around 18 or 19 features, and then we're predicting this 0 or 1 added to cart. So the very first thing, well, actually, before the very first thing, I'll kind of talk about my approach here. So I'm going to go through feature selection, feature extraction, feature engineering, and model selection. There's other ways in which you can approach classification tasks, but I won't go into that. So the scope of this talk is just for these 4 different approaches here. So the very first thing that we can try to do is kind of what we had before, which is create or replace model, right? We have options, logistic regression here, and we select country and total page views. And then let's see how well this performs. So here, I'm going to be kind of displaying a table for all the different models that I will be creating. I've created, and then I'll show you the results, so you kind of get a sense of the different kind of ways in which you can improve your models. So the first thing that we created was this log-reg model. It had only a few features, right? And so we had the log loss and the ROC AUC. So if you're not too familiar with either of these, the log loss is error, okay? So the lower log loss is, the closer it is to 0, the better the model is. ROC AUC, the closer it is to 1, the better the model is. And this is these are 2 ways in which you could kind of compare between models. They're not absolutely perfect. So, if you're a statistician, you could have lots of discussions about this, but these are in general 2 different ways in which you could kind of compare between models to see if one model is doing better than the other. So again, in kind of overall, log loss, we want it to decrease, and ROC AUC, we want it to increase towards 1. Okay, so that is essentially our baseline, right? We've only trained it on just a couple features, not very exciting. Let's try to use some more features at the very least. Let's try throwing all the features at logistic regression on BigQuery and just try to see what happens. All right, so we have create or replace model, and here what I'm just simply doing is I have the prefix for logistic regression here, and then I say _all just to keep track of exactly what the model is kind of in the name of the model itself. So it helps me keep track of things here. And of course, I'm selecting all the data here, and I'm using the except syntax here to remove the full visitor ID from that particular select star statement. So let's see how well this performs. So logistic regression all, using all the features. Now log loss has increased a little bit. Okay, so from 0.120 to 0.124. ROC AUC has oddly increased as well, so 0.951 to 0.953. But we kind of know that we kind of looked at the schema together. We know that probably just using 2 features probably isn't enough. The more features we probably use and kind of have it trained, using more features to train the model is probably going to be better. So it could be that some of these features are not super important, or there's probably quite a bit of noise by adding in more features here. So that's probably why the log loss increased. But that's just kind of a hypothesis. Let's try to do some more things to try to improve our model. So what's the next thing that we can do? Well, we saw the date column, and we also saw the visit start time column, and there were some issues with that. And the key thing is that, so number one with date is, why don't we just choose the ones that we think, the features within the date column that we think are most important. So for example, the month, the day of the week, the day. So if it's February 1st, 2020, the month would be 2, and then the day would be 1, and the day of the week would be Monday, Tuesday, Wednesday, or Thursday, and so on. Of course, you could also add in here weekday versus weekend, because essentially people could change their behavior a little bit depending on the day of the week, the day of the month. Maybe certain months are more popular in terms of shopping online as compared to other months as well, right? You can imagine holidays and so on. And then finally, for the visit start time, because this was in a epoch kind of time, Unix-based time, we converted that into a timestamp format. And then from there, we extracted out the hour. So here, hour is extracted out. And we're not extracting out minutes, because you can imagine, the 33rd minute of the hour versus the first minute of the hour may not have a huge impact. So I decided not to use that. And of course, through all the other variables in as well, except for date, visit start time, and full visitor ID. So given these new date and time features that I've now added to the training data set, how well does this model perform? But before we talk about that, this is actually going to create a bit of a problem. And I don't know if you've kind of noticed this. So essentially what we're doing here is we're selecting new features, that we're kind of creating new features in the select statement. And this is going to be a problem, because if we were to use ml.predict, we have to keep track of every single feature that we create in the process of creating the model. So ml.predict, we now have to remember, oh, we extracted month. We also extracted day of week and day and hour for this particular model. And that's going to be a little bit difficult to keep track of. So that's going to be very kind of frustrating to do. So in order to circumvent that, what you use is transform. So what transform does is, so anything that you list here under transform will be used and kind of remembered within the model, so that when you use the ml.predict, it will only use whatever you kind of told in the transform, even though you don't specify all the pre-processing features. So when you use transform with create model, the model will remember your transformations when doing the prediction. So you essentially don't have to extract twice in your create as well as your ml.predict statements. So here you can see select star from project dataset train. That's kind of the data that you're drawing from. You're making transformations on top of that. And so ultimately the model is trained on the data that you specify within transform. So here are the features that you end up transforming and you end up training the model on. So when you end up using ml.predict, you can simply do select star, as long as it contains all the features that you used in the transform for your create model, then that is completely fine. So that makes things a lot more consistent, a lot easier. You don't have to keep track of the same thing twice between create model and ml.predict. Okay, so what did we just do? We just extracted date, and we also extracted time. So how well does this model perform? So we see that log loss has now decreased from the large register all. So that's a good sign. Error has decreased. And ROC AUC has actually increased a little bit by about 0.001. So that's also going in a good direction. But what are some other things that we can do to try to continue to improve our model? So we noticed that there was a lot of string columns. So for example, a traffic campaign, it said, AW dynamic search ads whole site. And it also had some ones that were like not set and so on. So you can imagine in your data sets, you might have a lot of, descriptor columns that have lots of text in them. So how do you kind of extract some of this text data from these text columns? And you can see here on the right-hand side, I use a select distinct from this data set here. And here's, lots of different traffic campaigns that were used as part of the Google merchandise store here. So how do we extract more insights from this? So you can use regex extract all. So what this does is you put in a column, a string column that you want to kind of extract the words from. You specify a regular expression. So here I'm specifying any word that contains at least one letter between lowercase a to z and uppercase a to z with at least one of these letters, which is what this plus sign means for this regular expression. And by doing so, now I can extract all the words within traffic campaign. So you can see here on the right-hand side, not set becomes not, and then set, all products. Well, it's fairly straightforward here, right? So this is one way to extract kind of data from text-based columns in BigQuery. The other way that you can do this is actually using n-grams. So you can imagine in some cases, the word order is actually very, very important. If you only draw out single words at a time, they're called unigrams. They may not, retain the order of the words, and that might actually be very important for your particular use case. So for example, this is a common kind of way to describe n-grams is if you have a sentence like, I live in San Francisco, you could draw out all the unigrams. So I, in, live, Francisco, San. These are all in alphabetical order. Or you can also draw bigrams. So bigrams is where n is equal to 2, where you can say you want I live in San and San Francisco. And this might be important because you might have other cities like San Jose, San Diego, and other San-related cities. And so maybe that's really important. You don't just want to draw out San because that's not really going to encapsulate the city name or the name of the city. So that's really important to keep that bigram in together. So you can use that in BigQuery and BigQuery ML directly. So on top of regex extract all, that was taking in all the words, the individual words. You can actually use ml.ngrams on top of that, and you can specify the number of so the n that you want to draw out. So in this case, we want all the unigrams and bigrams. As an example, you could choose 3, you could choose 4, and so on. So here you can see the resulting here on the right-hand side is from not set, you get not, set, and not set. So the unigrams as well as the bigrams. And you see that for every single row as well. So just a couple lines of code here, and we've drawn out both the unigrams and the bigrams from our text-based columns. So how does this perform? How does this improve or not improve our model? So we can see here from the row 3 to row 4, we now go down actually a little bit for log loss from 0.122 to 0.121. So that's great. The error is actually decreased. We've actually drawn some sort of a signal out. And the ROC AUC has actually decreased 0.9545 to now 0.9538. So something is going on here. So maybe n-grams is not performing as well as we'd hope so. So this could also be due to random chances alone. Always remember this when it comes to log loss and ROC AUC. The further kind of in terms of decimal places, there's also this sense of random chance as well. So it could have been overfitting, could be underfitting, or not really generalizing well. So always keep that in mind. But in terms of log loss, decreasing ROC AUC, increasing, so that's a mixed signal, n-grams may or may not be doing well. So let's try to investigate that a little bit further as we continue to create more models. So what are some other ways that we can kind of improve our model? Well, we dealt with string-based columns. What about numeric-based columns? So for example, if we have a total time on site, right? So you can imagine someone spends 1 second on the Google Merchandise Store, or 15 seconds on the Google Merchandise Store, or 101 or 345 seconds, which is about 6 minutes on the Google Merchandise Store. So in those instances, you can imagine maybe the people who are spending 345 seconds and 346 seconds are actually doing roughly the same kind of behavior. They're kind of spending this similar amount of time on the website. So maybe we should kind of group them together into the same behavior. So to group them together, it means to bucketize them or to bin them together. So you can use something called quantile bucketize. You specify how many buckets you want, and it will automatically create a new feature to create a new column that will bin that numeric column into its own kind of category-based feature. So now we have bucket underscore total time on site. And here we have all the bins which correspond to certain ranges of total time on site for this particular column. So now with ML quantile bucketize, you can see, for example, in the very first bin, bin 1, we now have 382,000 rows that have now been allotted to the first bin. 3,500 rows are now kind of correspond to bin 2, and so on and so forth. So you kind of see there's a bit of a distribution. Most of the people seem to be spending very, very little time in that kind of bin 1 kind of category there. But nonetheless, we can try to use this and see how well this improves our model. So what we did was, or what I did was I used bucketize on all of the numeric columns and added that as part of the training data set and try to see if it improved. And you can see here actually from the second last to the very last row, the log loss has now decreased quite tremendously from 0.12 to 0.09. And the ROC AUC went from 0.95 up to 0.97. So both in really great directions, indicating that bucketize for this particular data set was actually very, very useful. It seemed that helped to draw out a lot more signal from the noise, so to speak. And so bucketize seemed to be doing very, very well. Now, we've talked a lot about different ways in which we've pre-processed the data so far: string columns, numeric columns, dates, and so on. And so what about using different kinds of models? Because we've been using logistic regression so far. So there's other models available in BigQuery ML, XGBoost, DNN, and AutoML. So the differences between these four, I'll just kind of go through them very quickly. Logistic regression tends to be the simplest, but the very fastest, like absolutely the fastest between these four. XGBoost tends to be better than logistic regression, but quite a bit slower than logistic regression. Deep neural networks also is slower, even more slow than XGBoost, but it can sometimes perform better than XGBoost. Sometimes it actually performs worse. So it really depends on the hyperparameters that you choose and so on. And then finally, AutoML can be slow to train, but performs very well. And furthermore, AutoML doesn't actually require your human time because you train it and you let it run, you do something else, come back, and then it's done. So it's a different kind of mode of training. So let's try XGBoost, and then we'll try deep neural networks afterwards. So first with XGBoost, you can see here at the very top, I'm changing this from LogRidge to XGB. This, again, is just to keep track of the names of the models. And I've changed model type to boosted tree classifier, but you can see everything else is the same. I'm using all the features, but more importantly, under transform, I'm extracting out the month, day of week, day, hour, and time in terms of the hour as well. So same model as before. Let's see how well this runs. So you can see here, the very first row is the best model that we had from logistic regression. And that was LogRidge all extract date with the n-grams, doing all the bucketizing as well. And that was 0.09. But with XGBoost, already you can see it's further improved the log loss, decreased it down to 0.07. ROC AUC has also increased up to 0.983. It's crossed that kind of 0.98 threshold, which is great. And then further on top of just extracting the date, I've also done bucketizing for all the numeric features. And again, that also further improves the log loss and also increases the ROC AUC. Now, one thing that I want to note here is I actually removed n-grams from this table because I noticed by using n-grams, the log loss and ROC AUC actually kind of performed worse. So n-grams was actually not doing well in terms of the XGBoost model. So that actually made things a little bit worse. So I've removed that and only used bucketize and extracting date. So that kind of helped the model there. So those are results for XGBoost. But there's actually something else that I wanted to touch on, which is what happens if you have features where you want to kind of find the intersections of those features to understand the interactions of some of these features. Now, let me just kind of explain that a little bit further. So you have total hits. Okay, so we have total hits as one column. We also have total page views as another column. What if we were to find the interactions between the two? Because it could be that, it could be one column and you have column B, but the interaction between them could actually generate more signal than any single column alone. So in that case, you could use something called polynomial expand. So by specifying the columns that you want to combine together, you can specify also the exponent that you want to kind of expand into. So here we're selecting 2. Now you can see it creates new features. So from total hits, it also creates total hits times total hits, which is 28 multiplied by 28, or 28 squared, which is 784. It also multiplies total hits by total page views here. So this is 28 under total hits multiplied by total page views, which is 22, to become 616. And of course, it also does the final thing, which is to square total page views as well here, 484, which is 22 squared. So you can imagine you can also add in more features here and do multiple crosses. And you also increase the exponent from 2 to 3. So by 3, essentially you're taking the cubes of total hits and total page views and doing all the possible combinations between the different features to generate more features. So that's also another thing that you could do as well. But here I'm just selecting 2 features at a time and just simply using 2 as the exponent. And that is for numeric type columns. You can also do this for string-based or categorical columns as well, using feature cross. And simply what this does is it simply concatenates those columns together. And just in terms of the intuition here, just to kind of make sense of it. So imagine that you have users in Singapore, and you have mobile users and you have tablet users. It could be that mobile users are more active for some reason in Singapore compared to tablet users. Whereas perhaps the opposite is true in maybe Latvia. Maybe tablet users are more active than mobile users. And so for that reason, finding that third kind of column here where we're getting the interaction between those two features, Singapore mobile and Latvia desktop and so on, maybe that can give us a lot more information than any single column, the country or the device category could have given us alone. So this is the reason why you might want to consider using ml.featureCross. And again, you can choose the number of concatenations that you want to have here as well, and the number of different columns that you want in featureCross as well here. So one question you might have is, well, I simply selected total hits and total page views almost quite manually here, and country and device category manually here. How do I do this more at scale? How do I do this programmatically? How do I find all the columns that are numeric, or how do I find all the columns here that are string based? Well, you can actually use that using information schema.columns. And by doing select followed by column name data type and using information schema columns, you can find all the column names that are string based and all the column names that are int64 or float based columns. So you can use that, then pass that into another SQL query, or it could be with dynamic SQL, or if you're using a Python client library to generate your SQL statements. This is a great way to be able to dynamically create your SQL statements on the fly, regardless of actually the true number of column names that are string or numeric based. So that's what I did to help kind of identify them. And so using polynomial expand to run on numeric features, you can see here from log loss, I've actually decreased it now further from 0.0728 to 0.0724. And ROC AUC has then further increased a little bit as well in the 4th decimal place here. In the final row here, I'm doing XGBoost polynomial expand. And then on top of that, I'm using feature cross on all these string-based columns. And here you can see, again, log loss has decreased and ROC AUC has yet again further increased a little bit. So also kind of improving the model for XGBoost in both ways for polynomial expand and also for feature cross. At this point, you might be thinking, okay, what about deep neural networks? We haven't really covered that yet. So again, changing the name to DNN and model type to DNN classifier. You can actually specify the number of layers and the number of nodes that you want per layer and so on. Here, I'm actually just leaving it as default, but that's something that I would do if I were to try to continue to prove this. But leaving it as default settings, let's see how well deep neural networks does compared to XGBoost. So this is here the best possible model that we had created so far between logistic regression and XGBoost. Now with deep neural networks, you can see using extract date plus bucketizing the numeric features, our log loss has further now decreased to quite significantly to 0.06, and ROC AUC has now increased again from 0.984 to 0.987. So that's, I guess, a fairly substantial increase compared to the marginal increases that we saw before. So this is great in a really positive direction. But you also find that if you run this with extract date only, so without using bucketize, you find that log loss actually improves quite a bit further from 0.06 to 0.05, and ROC AUC also improves quite even actually more dramatically from 0.987 to 0.989. So actually removing bucketize somehow improved the performance of deep neural networks. And you can kind of discuss and kind of think about why did deep neural networks kind of perform better with less features in this particular sense compared to XGBoost. Well, it turns out that it could be because of the way that deep neural networks and XGBoost kind of works in terms of how the model trains. XGBoost does really well by kind of splitting the data and creating trees that way. And XGBoost does really well if you have lots and lots of features. Deep neural networks will actually do very well in extracting its own features, doing its own feature engineering in terms of the way that neural networks work. So it could be that deep neural networks, you don't really have to do as much feature engineering compared to XGBoost. And maybe for that reason, just by extracting the date was sufficient. The date and the time was sufficient for deep neural networks there. So that is the best possible model that I was able to create between XGBoost, logistic regression, and deep neural networks. And so far, as I've talked about, these are the different approaches that I tried with this particular classification problem: feature selection, feature extraction, feature engineering, model selection. But of course, as I mentioned, I didn't try to do any sort of hyperparameter tuning, and also didn't try any model ensembling as well. And model ensembling is more about kind of, it could be that multiple models combined together could achieve better results than any single model alone. It could be due to generalization or overfitting. So I didn't try any model ensembling in this particular for this particular session here. So at this point, you might be thinking, how does AutoML perform here? So in order to train AutoML, it's actually very easy. So again, just giving it a name here, I'm specifying AutoML and the number of hours that I want AutoML to train for. Specify for model type is AutoML underscore classifier. If you're doing a regression problem, it'd be AutoML underscore regressor. And then for budget hours here, I set it to 1.0, but I also trained it for 2 hours, 4 hours, 8 hours, and 12 hours, just to see if a 12-hour AutoML model would actually outperform a 1 hour AutoML model. 1 hour AutoML model, meaning that it was trained for just 1 hour. So again, selecting all the data, just kind of dumping in, as in doing no feature pre-processing whatsoever before feeding it into AutoML. So let's see how well it performs. So this is DNN, and then followed by the AutoML row here, and then in the bottom row here, just trained for 1 hour. And you can see AutoML actually outperformed the deep neural network. So log loss went from 0.058 to 0.057, and ROC AUC increased. This is now in the 0.99 threshold now, so 0.989 up to 0.991. So the AutoML model actually outperformed the deep neural network model just like that with training for 1 hour. And then here I have the results for 2 hour, 4 hour, 8 hour, and 12 hour. So you can see here, It might be a little hard to read through all these different rows and all these numbers, but essentially if you look at the 12-hour one, 0.055 compared to 0.057 or 58 from before, and then in ROC AUC 0.991545 compared to 0.991015. So by decimal place, AutoML, the 12-hour one wins. But again, just bear in mind that, it could be just due to random chance here a little bit, but it seems like overall, at least it's in the right direction. Actually going from 2, 4, 8, 12, generally speaking, it actually does seem to improve in both log loss and for ROC AUC. So the longer you train AutoML, the better it seems to perform. And also, even the AutoML model that trained for just 1 hour essentially beat the best model that I tried with XGBoost and DNN. But of course, given the scope of what I tried, maybe, with hyperparameter tuning, I could have beat AutoML, but, we'll give it to AutoML in this particular case. We also, interestingly enough, tried to run an internal hackathon at Google as well, just to help train people with BigQuery ML internally and so on. And we had about 10 teams try to compete to try to create the best possible model. Again, it's same problem, so on. And here we have 10 teams here. And again here, AutoML, even just trained for 1 hour, beat the best possible, beat the best human team here. And of course, that being said, the human teams only had about an hour and two to actually try to create the best possible model here. So of course, I would say AutoML actually outperformed the humans there. But I guess that's another point for AutoML there. So 2 points to AutoML and none for humans so far. But it turns out, actually, the AutoML product teams, the engineering teams at Google, they try to use AutoML in the actual calculus competitions that were actually public. We had thousands of teams in these public competitions. In this one particular, around fraud detection, they try to use AutoML. And it turns out that for the first 12 weeks of the competition, AutoML came in the top 15%, but it wasn't number one. And then at the very end of the 12 weeks, ended up in the top 40%. So it wasn't close to, the top, it wasn't in the, the 39th. And so on. So AutoML actually lost to humans in that regard. So 2 points for AutoML, 1 point for humans. So at this point, you might be thinking, okay, in this case, so how do you choose between AutoML versus building your own model or a DIY model, do-it-yourself kind of model, not an automated machine learning model. So I would say use AutoML if you're looking to check if there's signal in the data, if you're trying to seek some sort of benchmark in your data, in your machine learning models. And AutoML could potentially save you some time and money. And especially if you don't really understand the data very well, if you lack that kind of domain expertise, AutoML could give you a good kind of starting point. But the problem is it's not auditable. So build your own models if you need to explain your models. And if the model performance is your absolute highest priority and you have that time and expertise, you could actually potentially outperform AutoML there. So summary, we went through lots of different pre-processing features, different models, and how you can build them in BigQuery ML. And finally, we covered when to use AutoML versus when to kind of DIY or do it yourself, bring your own kind of model sort of thing. So hopefully, I know I'm a little bit over time, but thank you so much for listening in. And hopefully that was helpful to you. I know it was a bit of a whirlwind. I spoke quite fast, but hopefully that was helpful to your machine learning use cases at work or in your projects.
Yeah, thank you, Polong. It was definitely very helpful for me in my work. So I'll definitely be taking a look at this again. It was very interesting and great how to use AutoML and when to use it. Actually, it's a pretty good insight. So thank you so much for this talk. Very good talk to ending. It was excellent. Thank you. Hope you had a great time with us today.
Great. Absolutely. Thank you so much for having me then.
Yeah. Awesome. Cheers. Well, thank you so much for joining us. This was the last talk. Me and Pranav are going to close the sessions. It was pretty interesting, huh, Pranav? Have you learned anything today?
Very interesting. Polong went very deep into machine learning, and to be fair, as an individual who's just learning about the basis of machine learning, I found it very, very interesting.
Yeah, definitely. The fact that you could just go to AutoML and get a quick model, that's great. And then you could just do it yourself, as Polong said. So yeah, let's just be in charge of the outro. Well, this is the agenda. I think we added something at the end.
Yeah, so there's a comment I can just show on screen.
Yeah, there you go, guys. So you can join us in a after party. We'll be there from now on. You can join us, have a quick chat, revive those good old moments. And yeah, you could just reach out, enter, and talk with the speakers. Let us know if you have any questions or anything. So great. Thank you so much for today. I just want to take this time to thank all the hosts and speakers who did a nice and excellent job today. And also everyone who joined. Thank you so much. And well, looking forward to doing more talks and more events with us. Yeah.
Yep. Thanks, guys. Thanks for tuning in.
Thanks for tuning in. Bye-bye.
Peace.